name. I think it needs a new name, and you'll see, I think, on your own why that is the case and why it might be trivial, but you'll see. We need to rename it, and we've been sort of gaslit a little bit, misdirected slightly, which has done quite a good job of us not really being able to just quite get over the line. So this 6.2856, and this fourth decimal place here with a 6, it can go between, it's the fourth decimal place, remember, so when you're looking in practical terms, you can't see that. You cannot see this tiny fraction unless the circle gets very big, and then of course these little fractions here become more visible. In practical terms for building, these things are important. Physical building of objects. The little variations on a guitar matter, like millimeters, will put you out of tune. So on an instrument, it matters in millimeters. On a giant pyramid, an inch here and there, no one's going to fluff about it. We know what the numbers really are. They're the whole numbers. So, but anyway, I want to show that there is this sort of magic in a circle that has this variance, and this variance is very interesting, and it gives us a lot more than we ever kind of dreamed. So let's just start with, the radius of 1, the circumference will be, of course, 6.2856. Well, that's 2 pi r. So, of course, with a radius of 1, the circumference will be that. Now, it's such a small scale. 6.3 also has a radius of 1. So these two here, it's so small that when you punch it in with 2 pi r, or the usual calculations that we're used to, even though we'll see they're not accurate, and we're going to get the true accurate definition of pi. So now we're going to scale up from 1 to 10. And now we get to 10, we just moved the decimal place to, instead of 6.2, it's now 62. 62.856. And the radius is 10. Stays the same. But the 63 now, instead of 6.3, the radius has actually grown a little bit by 0.03. Okay? No worries. But I would have thought, just logically, that would have just remained 10, But anyway, then we keep going up to the next. And this is actually our string length scale size now. We're at 630. So 630 millimeters string length, which I've already shown. We're at that scale now. So now the radiuses have grown a little more even with this 628.56 now. We've moved the decimal over. Even he's grown another 0.1. So 630 is now the radius is 100.27. The difference between these two now, at this scale of 630 and 628.56, at this scale, we're not down at 6.2 now, we're up at, we've grown just by moving the decimal. The difference between here, and this is now string length, the difference is 0.23. 0.23. Now that is the difference between these two radii, but it's also how many cents, they call it, cents in the Pythagorean comma, which is where the notes, you have to do some music study, not a lot, it's very quick, but you'll see that there's a problem with the music thing, it doesn't quite reach the equilibrium, so it's called the Pythagorean comma. It's got other names as well, but it's very interesting, isn't it, that our 23 cents matches our radii here once we're at string length especially, so I was curious. But we keep going. And also the difference between these two, 630, this is our magical string length of an instrument. And you see in the other video, it gives us all the planet synodics and all sorts of things. But the difference between these two is 0.144. 0.144. Anybody that knows anything about this sort of stuff knows that 144 is the magic for many things. Won't go into it today because I'm sure many people already understand lots about 144. But in future episodes you're going to see umpteen amounts of things on that. So the next part here is, we've covered this in the interview with Ryan, but we need to just preface where we're going somewhere, okay? So we got in the interview with Ryan, in the presentation I showed, that the column of D, right? Now this is the Pythagorean harmonic series. But this is just the column of D, because what I discovered from Howard Crowhurst, he gave us the measure from the Great Pyramid to the equator, and it was 3,317,760 metres. And he finds a lot of metres in the ancient world, and of course there's no metric back then, we're told. So, you know, we're going to see that that's not the case, that he's right, there was metric all the way back then, because they're all derived from each other and there's a method to do it. So Great Pyramid to the equator is 3,317,760 metres. That is also in megalithic yards. Now, when you look at the Pythagorean harmonic series, this is actually megalithic yards. It's 0.82944 of a metre. And it's also the note of E, and it's the very last note in the Pythagorean harmonic series. The last E is 82944. So, as I was showing in the last, a few months back with all this, is that Melissa and others have we were all very curious about how D was somehow linked to meters. But it was all very exciting, interesting and curious. But where's the linkage? Like John Neal was saying, they've written lots of books on all this stuff. We're still missing something that links it all together. Today we have it. We have it. Sounds like a big claim, but we can demonstrate. So, what I discovered after I saw Howard's video, and he gave us this measure, 3 million, right? I realised that the column of D, 9 hertz times 36,864. You times the first one and the last one. You get the Howard Crowhurst number, equated to the Great Pyramid. Then we just go down to 18 and we come up one, right? Same again, same answer. We go down to this one, 36 times 9216 again. So this continues until we get to the middle, right? Now the equator is obviously the middle, Mies. It is, the Giza was said to be the centre of the landmass, another centre. Now what do we put in the centre? Yep, it's the obelisk. It's Osiris shaft. This is what it is, but it's upside down when we look at it at Washington. The pointy bit's at the top, that's pointing it at the sky. We just do this, and you do, because you'll see.